really long chapter. But we are on the last section of the chapter, which is kind of a strange one because it seems like it should be the first of the next chapter. I'm not quite sure what the teaching strategy here is, but for whatever reason they put this material on the end of this chapter. After today, then my plan is on Thursday we're going to have a review session. And between now and then I'll also get a sense as to what I want the test to look like and stuff like that. And we'll either do the test on, see, this is not a week where you guys are on Friday, so it'll either be the next Tuesday, or maybe it'll be a take-home thing or something like that. I haven't decided what the right strategy is about that yet. I need to take a look as to how many days you guys have left, because it's not just tons. Yeah, I think you have like 3 weeks or something like that. And I want to make sure we make progress on the next chapter, because it's kind of important to calculus. But so is what we're doing today. So far, everything that we've done in this class that was calculus was derivatives. And once we got the hang of what derivatives were, we were happy. I mean, doing derivatives was almost, dare I say, fun. Where we, took some kind of function like f of x, and, let's just say it was 3x cubed, and we found the derivative of f of x with respect to x was, in this case, 9x squared. And then we learned lots of ways to do this. I mean, like product rules, quotient rules, power rules, the log and exponent rules, chain rule, all those friends. Okay, all of which will be, this was the chapter we learned all that stuff, wasn't it? Didn't we do all that in this chapter? This has been a heck of a long chapter, good grief. Anyway, okay. Gosh, I can't even remember. Was that all in this chapter? I think it was. Where are we at here? No, those those were in the last chapter. This is the linear approximations, finding maxima and minima, the derivatives and shapes of a graph, mean value theorem, all that good stuff. Okay. All right. So what we have been doing here was taking the process of taking a function and finding its derivative. In the final section of chapter 4, we're going to be doing the opposite of that. We're going to be taking some function, f, and saying, what function could this thing be the derivative of? So if we had some function like f is 3x cubed, the question is, what function could that be the derivative of? In other words, we want to find the antiderivative. Derivative of f. What function would have had this as its derivative? Right off the bat, you can see something we're going to be able to do to check our answers really well. And that is, once we think we have the answer, we could take the derivative of the answer and make sure we get this original thing back. Okay, so if we were looking for some kind of definition, like if you're saying given some function f of x, big F of x is the antiderivative of little f of x if big F prime of x is little f of x. In other words, if the derivative of that big F is equal to the function you started with. Let's do an antiderivative to see what the pattern or whatever is going to be. For example, if I had a problem, f of x is equal to 3x squared. Okay. We want to find the function that is the antiderivative of this. Alright. So, what are we going to do? Well, now I'm going to tell you that in the next few minutes I'm going to show you some rules to this, but we will find out that this is x cubed plus c. And I'll show you what that means in just a little bit. But I'll be showing you the rules on how to do that in just a second. But the first set of problems that you're doing in the book are verify that big F of x is the antiderivative of little f of x. So like you would have problems like this. How would you verify that this is the antiderivative of this? what I would do is then say, well, what is f prime of x? Because if I take the derivative of this one, it should get this one. Well, the derivative of this would be 3x squared. And whatever this constant c is, this c is just some constant that's going to be back here. Whatever this constant c is, a derivative of a constant is just 0. So one thing you're going to see about antiderivatives is they always have this plus c on the end. That means any constant we added on here would be fine. Okay? When you could do the antiderivative, you always have to add that c on the end there. All right. How did I get this? Let's do a simpler one first. What if my function that I was finding the derivative of was just x squared? I'm sorry, I'm trying to find the antiderivative of. I like to picture this as sort of like, I don't know, in my mind, it's kind of like a mountain. And f of x is here, and big F of x is up higher on the mountain. We could take the derivative to go here, or the antiderivative to go up here. The antiderivative is a higher power. Right? Just like taking the derivative of something lowered the power by 1, taking the antiderivative is going to increase its power by 1. Right? Okay, I don't know, I always picture it like a hill. I don't know why, that's just the image I have in my head. So I know my antiderivative of this, which is going to end in plus c, go ahead and write that first, because that's important. You're going to see why in the next chapter. So we know it's going to be something plus c. And that something is going to involve x cubed. Because we know that, just like I said before, by taking the derivative, the power is going to go down by 1. So by taking the antiderivative, the power has got to go up by 1. So then the question is, what does this coefficient in front of here need to be? Well, when I take this derivative, it's going to be whatever this is times 3. And it's going to have to equal what the coefficient here is. Well, right now, this coefficient is 1. What times 3 will give me 1? It's going to be 1/3. So 1/3 x cubed plus 3 is the antiderivative of x squared. How will we prove that to ourselves? Take its derivative. The derivative of 1/3 x cubed plus c is 1/3 times 3x squared, that'll cancel out, plus 0, or just x squared. There's a power rule here. Just like there was a power rule for taking the derivative, which was so simple we actually didn't really need to write it down, the antiderivative has a power rule too. If you have a function that is like x to the n, the antiderivative of that is just 1 over n plus 1, x to the n plus 1, plus c. So we started off with x squared, so n was equal to 2. So our antiderivative was 1/3 times x cubed plus that constant. Whatever that constant needs to be to make the problem work out, as you'll see in the next chapter. But for now, we need to just be a constant. So we have a power rule. To make these things work.
Is that n plus 1?
N plus 1. N plus 1. 1 over n plus 1 times x to the n plus 1 power. Here's another rule that will come to you as being familiar from when we did derivatives. What if I had this closer to what the original problem was? What if I said it was 3x squared? Hey, you remember when we did this with derivatives? When we did this with derivatives, if there was some coefficient in front of the part that's a function here, like x squared, we could just take that coefficient out and just do the derivative of this part out here. The fancy way of saying that was like, if f of x was like some constant times, no, let's do it this way, times g of x, then f prime of x was just that constant times g prime of x. That constant out in front, we didn't take the derivative of that, right? It just went out in front. So like if f of x was 3x squared, f prime of x was just 3 times the derivative of this, which was 2x. So this was 6x. In the same way, we can do exactly the same thing with antiderivatives. If we're trying to find the antiderivative of this, big F of x, it's just going to be 3 times the antiderivative of the x squared, which again, we had the antiderivative of that was 1/3 x cubed. So this 3 came out, and then we did the antiderivative of the part that's a function of x. So in this case, it works out to x cubed plus c. And we could test that if we wanted to. If f of x was equal to x cubed plus 1,000,000, f prime, I mean that's a good value of c, then f prime of x would be 3x squared. And that's what it was supposed to be. Yay! I can't think what the rule is called, but we can have a coefficient out in front. Coefficient, I don't know, I can't spell. It can't have a coefficient out front. We had exactly the same thing with derivatives. We can just do the exact same thing with antiderivatives. Alright. Another thing you can do with, and we're going to write those rules in a better way in just a little bit. What if your function has terms? For example, what if our function was 3x squared plus 2x? There's 2 terms. You guys know that vocabulary? Terms are separated by plus or minus signs, right? So we've got 2 terms here. It's a polynomial. Okay. The way it works is you can compute the antiderivative of this part, and then you add the antiderivative of this part. Exactly like we did when we did the derivatives. Remember when we did the derivatives, I mean, as the equations got longer and longer, it didn't really get any harder, right? I mean, we just did the derivative of this part, plus the derivative of this part, plus the derivative of that part, right? It wasn't any harder. We can do exactly the same thing. So here, our antiderivative of this expression will just be the antiderivative of this guy, 1/4 x cubed, to the 4th power, plus 1/3 x cubed plus c. Again, we're just applying our power rule twice. This one and then this one. Exactly like we did it for derivatives. It's not even a new rule. I don't even know what the right word here is. We're going to call this sum. We're going to have better ways to write this out in just a minute. So these are not so big of a deal. As long as we're just talking polynomials. If f of x equals 3x to the 4th power plus x, the antiderivative will just be the antiderivative of this, which is 3 times 1/5 x to the 5th plus 1/2 x squared plus c. Then we can do some simplifying and so on. And we're happy. And honestly, it's almost, dare I call it, fun to do this where it's just powers. The powers are the no big deal part of this. Why are we going to be doing this? There's all kinds of problems that are going to involve the antiderivative directly. Like, for example, remember how you could have an equation that described the position of an object and its derivative was the velocity? Because velocity was just the change of position. And its derivative was the acceleration, because acceleration is just the rate of change of velocity. Well, in the same way, if you have an equation that describes the velocity, the antiderivative of that is the position. And if you have the acceleration, the antiderivative of that is just the velocity. So like for example, if you have forces, F equals ma. The force is acting on something, gives you the mass times the acceleration. You know the mass because you weighed the object in advance. You got the acceleration. I know how much force I'm applying to this pen because of the force of gravity, whatever. I can figure out how much it's accelerating. And then if I know how much it's accelerating, I can take the antiderivative of how much it's accelerating to find its speed at any given time. If I know its speed at any given time, I can take the antiderivative of that to figure out where exactly it is at that time, its position. Okay? More importantly though, this is all going to head towards integrals, and there's about a zillion things we can do in the next chapter about integrals. But before we do that, let's start. Here's the deal. Your book is going to do this notation of little f is your function, big F is your antiderivative of it. But there's a better way to write these things that your book introduces. And that's to call it the indefinite integral. This is kind of more of a notation thing, but it is a bridge to get us towards integrals, definite integrals, which is what we're going to be doing all through the chapter 5. Indefinite integrals are kind of the same thing, kind of, sort of, as antiderivatives. It's not exactly right, but they're sort of. Where we're going to say, if we have, we're going to need a symbol. The symbol for an integral you've probably seen before, it's this thing. It looks like a stretched out letter S. It in fact is a stretched out letter S, as I've heard. As Wikipedia and YouTube videos tell me. I've never actually double checked with a math textbook and seen that that's true. The integral of your function f of x, little f of x, I'm going to leave a little space here because I'm just going to go here, is going to be equal to that antiderivative plus c. Now let me make sure I'm using the same notation they are before I move any farther. Every now and then they surprise me with something. Hey, come back, wake up, computer. Every now and then they think they're going to come up with something to surprise me. Yeah, okay. But there's a little piece of notation here. You write dx. So the way we would pronounce this is we would say the indefinite integral of f of x with respect to x is this function. So like for example, the indefinite integral of x squared dx is 1/3 x cubed plus c. See how the x squared, by our power rule, became 1/3 x cubed. Now, what is that little dx doing in here? The little dx means like with respect to x. See, here's the deal. You know as well as I do, by being a survivor of math classes, that there will be equations that have more than one variable in them. There'll be x's, y's, and z's, or there'll be times, and there'll be whatever. Okay? You only integrate with respect to one variable at any given time. Okay, we'll learn about what that verb I just said, integrate, and so on, means. So this is like a notation that tells you which one. Okay? So in this practice, of course, there only was one. Now, another thing to understand. Think of the integral symbol and the dx over here as kind of like the opening and closing parenthesis. It's a notation that kind of keeps the two pieces together, like that holds together. You mean the integral of what's between there. Okay? I learned calculus from Father Ports, a Jesuit back at Creighton in 1988. And he told me, it's a Catholic thing, I don't mean that in any disrespectful way, like think of the first one, the symbol thing, as like the sign of the cross at the beginning of a prayer, and think of the dx at the end as the sign of the cross at the end of the prayer, and the stuff's in the middle of what you're praying for. Okay? Alright? They're kind of like that. You can't have the integral symbol without the dx at the end. Or dy if it's a y, or whatever the problem is, okay? Now, if you have flipped through the book, or you have looked at other math classes, or whatever, you might know more can be going on than this. I mean, there are problems where there's stuff here like this and there are numbers here. There are problems where there is more than one of these integral symbols here. And there's stuff in between here, okay? We will be getting there with only like 15 days left, of which only like 5 of which we meet. I'm not entirely sure how it works. But we are crawling before we can walk, or we're walking before we can run, or whatever the metaphor is, okay? We're just getting started here. What the hell is this little fish-hooky looking thing? It is a symbol that meant to, I think Leibniz is the calculus guy who invented that symbol, but I could be wrong. It meant sum, as in, not like as in sum, like I'm going to give you some money. Sum as in like summing things up. We will see why that applies later. Integrals and antiderivatives are kind of like adding up little pieces. But that's not yet where we are. That's not the interpretation we're doing just yet. But you have seen that little symbol before. If you look at the Constitution or the Declaration of Independence or something like that, and they write in there, remember how you saw this in grade school or something like that like Congress shall make no laws to tax without whatever, and you saw those things? It was just another way of writing the letter S back then. Okay? Those little long curly S things that looked a little bit like an F, but are definitely not Fs. They were just a slightly softer S sound that has disappeared from our language. Okay?
What?
Does any... What?
Like, that used to be like a normal thing for us?
Yes. Yeah.
Why don't we keep that?
Well, I don't know. It's cool. So you might have noticed that, like, you know, in the Constitution it says, like, Congress shall make no laws to ban whatever, blah. It's always written that way. Okay? In the handwritten whatever. Okay, that's what that thing is.
Dang, we need
Hey, I know another example of it. Does anybody in this classroom speak German? Or I took German in high school or something like that, okay? Well, in German, there's a letter that looks like that too. Like if you're writing the word street in German, it's Straße, which is written like that. But this symbol here is really an S with another S beside it, that they blended together to make it look like that. It's called an etset. But they still have that sort of curly S thing in their language. Anyway, that thing is an S. But we never call it an S or anything like that. It's an integral symbol. But now that we have the ability to write out indefinite integrals, we can be nicer with our way of writing things out, like these power rules. Our power rule was that the integral of like x to the n dx, where n is some number, okay, is 1 over n x, I'm sorry, no, let's fix that. 1 over n plus 1, x to the n plus 1 power, plus c. Or, we had that coefficient rule, where like the integral of some constant c times f of x dx, I don't know yet what that is the same thing as, let's not use c, because we're going to have a c another place. Let's call this b. B. I'm happy.
Cool.
B will be equal to b times the integral of just the f of x dx. In other words, if you just have some coefficient in front of a function, feel free to pull the coefficient out before you do the integrals.
Oh, that would make it easier.
Yes, it will. Another one, that rule about sums, told us that if you had the integral of f of x plus g of x plus h of x, whatever, dx, where these were just terms, x cubed plus x squared plus 3x, whatever, that you could break up. You can actually write that as just the integral of f of x dx plus the integral of g of x dx plus the integral of h of x dx, all of which will eventually have plus c's behind them. Now, a brief pause. Here's the deal. Again, remember, it can be very, very easy to screw this up. let me write you an example of what this could look like. So this could be like the integral of 3x squared plus 9x plus 7 dx. You would be forgiven but still lose points for thinking that means take the integral of this, you know, like that would be 3 times 1/3 x cubed, and then, oh, then let's add 9x, and then, oh, let's add 7. But here's the deal. Remember, the integral sign and the dx over here, they're like the beginning and ending parentheses. I mean the integral of this whole damn thing. Right? The integral symbol is the Father, the Son, and the Holy Spirit, and the dx is the closing Father, Son, and Holy Spirit. The whole thing in the middle is what you're praying that you get the right answer about. Okay? I think it's just sacrilege all over the place today. All right.
I mean, you have been talking about higher powers.
That's right. And higher powers. Very good. Here's the deal. Most of the time, textbooks try to steer you away from making that kind of mistake by, if there's a whole bunch of terms in between the integral symbol and the dx, they'll usually put parentheses around here just to make it less likely you will make that boo-boo. Okay? So that you'll understand, I mean the integral of the whole thing. Each of those individual terms, each one integrated. Not just the integral of the first one. I will try to be very careful when I do things like write tests and so on to make sure I do that. I'll be careful to try to warn you, but just in case they don't have to. Okay? The integral symbol and the dx. That dx is called the variable of integration. Okay. The stuff in between there is what you integrate. That stuff that is in between there that is what you are doing the integration on is called the integrand. In other words, the right way to notate this is integral symbol, integrand, variable of integration. Variable of integration. Now that we have some notation to go rock and roll on this, computer, I hate the fact that this thing falls asleep unpredictably and very hard. Much like my children in the evening. Sometimes they're still up at 9:30 at night, and sometimes, unexpectedly, they're sound asleep at 6:45 on the couch, and you can't wait up to go get a bath. You know what I'm saying? My computer is much the same. Once you have this, well, powers aren't the only thing that we have learned derivatives of. We've learned derivatives of lots of other kinds of functions too, like trig functions and exponentials and logs and oh my god. Does that mean all those things have antiderivatives or indefinite integrals too? They sure do. And you begin to see that on page 489, where there are these tables. I like the second column of the table better where it has the as indefinite integrals. But it has things, for example, like the exponent rule. Here, let me write that down. Exponent rule. Where it says the indefinite integral of e to the x dx. So here's your function. Your integrand is e to the x dx. Is e to the x plus c. You might remember that the derivative of e to the x was just e to the x. The integral of e to the x is e to the x. Or like, for example, there are some trig rules in here. For example, the integral of cosine of x dx is sine of x plus c. Again, think of it as works the other way around. The derivative of sine is cosine, so the integral of cosine is sine. And if you look on page 489 and forward, oh my word, there's quite the column of these guys. We'll have to make some decision about how many of these you need to know on the test, except the test is open book. Right? Here's the deal. I haven't looked around in this book that well yet. It's 10 days left of the class or something, I probably should have. But a traditional on-paper calculus textbook typically has several pages, like in the front and the back of the book, like on the inside, back, covers, and forward, with dozens, maybe hundreds of these integrals. Because here's the deal. There are these basic ones. The power rule, this exponent rule, this trig rule. There's maybe 5 or 10 of these it's worth your time to memorize. But math students, for the last 400-ish years, have been making more and more of these. Okay? And there are patterns to them and so on, where like the integral of b over x minus a squared dx, where b and a are real numbers, is equal to, let me just say, the log of b over x times a plus, I'm just making up that answer. But here's the deal. Some sad 17th century math student derived that, and it'll be just in the back of the book. And you get to use it. So if they give you a problem on your homework set that's the log of 7 over x minus 3 squared dx, you just go look in the back of the book to find the one that matches. Oh, I see, if b was 7 and a was 3, this is the same equation. So apparently it's the log of 7 over x times 3 plus c. Okay? So, the good news is, right now in the book, we're not going hog wild. There are just these, I don't know, maybe 10 of them or something on page 489. The first maybe 6 of them look to me like they're worth memorizing. But I can't force you to memorize them because it's going to be open book. But beyond that, they start becoming things like, you know, the integral of secant squared, the integral of secant times tangent, the integral of 1 over x squared. I mean, most of these, it's more a matter of can you find the right one for the problem you're solving. This is such a happy day for you. You are teetering on the edge of falling over the cliff of integration and learning all the wonderful things. That's a terrible metaphor. But it kind of feels like that. Like, man, we are just about to step out of that nest and fly and see all the cool kinds of problems you can solve with integrals and all the cool things you can do with them. But we have to survive antiderivatives first and this indefinite integrals. And then we have to actually take a test. Okay? But this will all be related to the problem of taking definite integrals, which definite integrals start off with the somewhat dry idea of like, here's a graph of some function, what is the area underneath here? That area will be, whatever that function f of x was, the integral of f of x is going to be about that area underneath there. And then it's going to turn out, wait a minute, there's only about a zillion problems that you can solve doing this. In many ways, integration is like math's happiest hour. It's the step that solves so many kinds of problems, from launching rockets to weather prediction to profits at a business to whatever. So much becomes integration. And we get like 10 days at the end of the semester to do it, but that's another story.
So wait, what is Calc? I know like Calc 1
Yes.
covers all this, but what does Calc 2 cover?
More! It goes all the way to Calc 4, and then they change the name and call it vector calculus. And then you do more about that.
I heard, is it true that Calc 3 is easier than Calc 2?
What is it?
Calc 3?
I would agree that I think Calc 2 is the fussiest. Calc 2 is where you, okay, if you were in, this would be basically, this class, Math 135 or whatever, I believe on the Ivy Tech side they call it brief calculus. Brief calculus is like Calc 1 without proving very many. Notice we haven't proved very many things. Most of the time we've accepted it on faith. We're back to higher powers. We've accepted it on faith. In general, we have not proven things. Brief calculus is like get through the stuff without actually worrying about proving much of it. Okay? Use it, don't prove it. Calc 1 is usually more proofs, but you also usually either get 4 or 5 credit hours for that, where I think you guys get 3 credit hours for this. Right? Calc 2 becomes a giant mess of problems about derivatives and integrals. in zillions of applications, all of which have exceptions. It's like learning past tense in your Spanish class, right? Suddenly, Spanish 1 was fun. ¿Dónde está mi maleta? Where's my suitcase? Right? And then you start learning that Spanish has like 4 different kinds of past tense, and oh my god, it becomes a giant mess, right? Spanish 2, nightmare. Spanish 1, fun. Right? Exactly. Much like that. Calc 1, kind of cool, fun. Calc 2, giant tangled mess of all the applications, all the exceptions, all the stupid stuff. Calc 3 then becomes more about like in 3 dimensions. How would you do an integral over a solid area and stuff like that. And vector calc becomes like over vector spaces and fluid motions and stuff like that. And yeah, oh my word, it becomes more and more fun. Well, it becomes more and more math nerd. Okay. Calc 2 is the fussiest in my opinion. But anyway, yay, we did brief calc. All right. I'm excited about this. Now, let me get the problem set here for you. Nope. 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 I have too many spreadsheets open. All right. There it is. Page 497. Problems 465 through 497 odd, and that is it. It's not one of the weird assignments where we're all over the place. Lots of the problems are written slightly differently, like they say, find the antiderivative of this. And then in another problem, they say, find the indefinite integral of this. At this level, there's not really a difference. Okay, they're basically the same thing. That plus C matters. Okay? The plus C is going to be important when we switch to definite integrals in the next chapter, so get the habit of doing it now, okay? Yay, this is cool stuff, trust me.
Habit.
What?
Not fun.
Habit! Oh man, it's been nothing but religion puns today.